Okay. Hello, everybody. My name is Bikramjeet. I'm part of the engineering team at Iceberg Engineering. Today, we'll be discussing the Portland's Toronto Development Project. So, on the project team is myself, Moore, Sophie, Aruma, and Anima.
The outline for this presentation is as follows. First, an introduction to the project, then the geotechnical and transportation methodologies will be discussed, followed by the innovative design, and then we will wrap things up from there. The project aims to develop Portland's region in a sustainable and innovative way with an emphasis on the geotechnical and transportation aspects of design and infrastructure. The Portland site is 325 hectares in size and was once a marshland that included wildlife. The ecological diversity in Portland has been affected by industrial use, shipping, petroleum storage, and crude oil refinery. Furthermore, the site is filled with sewage, construction debris, and municipal waste. The site is surrounded by 3 water bodies that include Lake Ontario, the Don River, and Keating Channel. There is significant groundwater and soil pollution within the site, which includes high concentrations of metals, inorganics, and volatile organic compounds. Certain major roadways such as the Gardiner Expressway and Lakeshore Boulevard are obstructions for potentially advantageous links that will help the flow of traffic. The major objectives of this proposed project include to recommend feasible foundation types for the construction of the bridge and to recommend design alternatives for new elevated expressway links with the Don Valley Parkway by removing the existing Lakeshore Boulevard Road east of Cherry Street. The scope of this project includes the following elements. For geotechnical services, the major elements are the site investigation and recommendations for feasible foundation designs, and then for transportation, the main element provided is a traffic impact study and preliminary design alternatives. The project will not include vertical alignments or construction design of the Lakeshore Boulevard Bridge.
Thank you, Aruma. So for the geotechnical methodology, we'll be looking at the soil analysis, the bedrock analysis, the foundation considerations, designs, and challenges. And Moore will talk about the soil conditions now.
Thank you, Bikram. Due to industrialization in the past, the site contains construction debris and waste, all of which lead to the area's poor soil conditions. Shown on your screen is a generalized soil profile for the location of the Lakeshore Bridge. As you can see, the largest SPT value after the fill layer is only 3, which is a large indicator of weak soil properties. Therefore, deep foundations will have to be used to reach stronger strata. The unit weights, undering shear strength, and friction angles have all been determined using correlation tables and will be utilized to determine the ultimate bearing capacity of foundation designs. Since the soil conditions have been proven not suitable, a bedrock analysis must be conducted to understand the bedrock conditions. Core samples were collected to determine the rock quality designation. Table 3.1 from the Canadian Foundation Engineering Manual was used to classify the rock with respect to RQD values. The table to the left proves to show that the bedrock strength increases with depth. The unconfined compressive strength obtained from point load strength tests were also used to analyze the bedrock. The values range between 35.3 to 82.4 MPa. An average value was taken and the point load index was determined using the formula shown on your screen. The results correspond to a grade level of R4, which indicates strong bedrock. The image on your screen shows the overall layout of the bridge. It will contain 2 abutments and 2 piers, each required to sustain loads of up to 3.75 meganewtons. I will now transfer you over to Bikram to explain the foundation considerations.
Thank you, Moore. So for the foundation considerations, shallow and deep foundations were looked at. Shallow foundations were deemed not acceptable due to the weak upper strata of soils and the high groundwater table at Portland. So the deep foundations that were looked at were driven piles, bored piles, and marker piles. Marker piles were eventually recommended by our team. Additional factors that were looked at were the existing structures nearby, the high groundwater table, and the high clay content. So what are marker piles? Marker piles are piles with diameter less than 300 millimeters. They can withstand high to moderate loads. The installation process is very similar to the drill shaft. So first you drill to the desired depth using a casing. You remove the drill bit, you install the steel elements, and then instead of using reinforced concrete, you would use grout. The grout would then transfer the loads from the reinforcement steel to the ground using friction. Since the diameter of the marker pile is very small, end bearing is generally neglected. Furthermore, during the installation process, there's very minimal disturbances caused because this is also due to the fact that the equipment used is very light and compact. So this is a typical marker pile rig, figure 2 and figure 3. Figure 3 shows a marker pile rig being utilized in the utility closet of the BMO soccer field. So the advantages were the main reason why marker piles were selected. Micropiles can be installed in difficult soils that are weak and have high groundwater table, which are all present at Portland's. Furthermore, micropiles can be installed in an area where there's low clearances, where conventional drilling might not be suitable, as demolition of existing structures will be needed, which will cause the cost to go up. But the main big advantage of micropile is the vibrations and the noise, which are very minimal during installation. This is key, especially when you're working in busy cities where there's structures nearby. When installing micropiles, the vibrations will be very limited. They won't travel through the soil, affecting the adjacent structures. Furthermore, the micropile sits at a small diameter. The installation process causes less spill and more control to the contractor, and dewatering is not needed for micropiles, unlike conventional piles, which it is needed for. So the challenges that were faced were first from the weathered bedrock. To overcome this challenge, the micropile will be socketed 3 meters deep into the bedrock in sound rock. The next challenge was the micropile installation method. So rotary percussive duplex method is very robust for drilling, but it's good for cohesion soils. For cohesionless soils, it's not good, and what happens is it causes blowouts and vibrations. For cohesionless soils, rotary drilling with drill fluid will be used to avoid any vibrations and blowouts. The last challenge is the contaminated soil. We know that Portland used to be an industrial facility, and it has a soil that's contaminated. So to prevent the micropile from corrosion, the reinforcement will be coated with epoxy and grout. And furthermore, the design calculation, the shell thickness of the casing was reduced by 1.6 millimeters to allow for any steel loss that might occur. And now more will talk about the design for piles.
Thank you, Bikram. The micropile design will consist of a 245 millimeter steel casing, 3 reinforcement bars with an area of 7,743 millimeters squared, and cement grout storing 35 MPa. The total skin friction is illustrated in the table with the value of 3,930 kilonewtons. As stated earlier, end-bearing contribution in micropiles is generally neglected. Numerous micropiles will be needed to sustain loads and prevent bending due to its thin design. The micropile grouping design will consist of a 4x3 matrix with a spacing of 760 millimeters. The first alternative is a drilled shaft. The design consists of steel reinforcement with a strength of 50 MPa and concrete with a strength of 35 MPa. The diameter of the pile will be 0.3 meters. The ultimate bearing capacity is illustrated in the table with a value of 6,416 kilonewtons. The pile is excellent for large loads. The installation process does not cause ground vibrations. However, it is difficult drilling piers and dewatering would be needed. The second alternative is a driven pile precast concrete pile. It contains the same dimensions and properties as a drilled pile. This is the only design that will not go to bedrock. As shown on your screen, the ultimate bearing capacity is significantly lower than the other two designs. These piles can be precasted to requirement specifications. However, transporting them to the site could be tedious. The installation process is noisy, causes ground vibrations, and requires a large overhead space. The decision matrix on your screen was used to systematically analyze and rate the performance of each foundation design. The results show that the most effective approach would be to use micropiles for the foundation of the Lakeshore Bridge. I will now pass it over to Aruma to go over the transportation methodology.
Thank you, Mayor. The transportation methodology includes a traffic impact study, evaluation, and design challenges. The traffic impact study consisted of retrieving traffic volume from the City of Toronto and inputting the data onto a traffic analysis software. Design scenarios. The base scenario represents the situation in Portland, Toronto for the year 2020. The vehicle capacity ratio, vehicle delay, and level of service were obtained for analysis. In general, the level of service is B or C for some of the major intersections. Future background scenario represents conditions for the year 2040 if no development is made. This is essentially a do-nothing case. It was observed that the traffic volumes have increased, delays have increased, and LOS typically has worsened. The year 2040 was chosen because it seemed tangible to model for years. 20 years later, technology is constantly advancing and it's important to keep up with that change. So beyond 20 years, there would have been various new infrastructure ideas emerging and Portland would have required revamping. The future total is the future background scenario with the addition of future development or land use obtained from Portland's plus south of eastern transportation and servicing. Trip generation, distribution, and assignment was used for this scenario with referral to the IT manual. The results were unsatisfying as the vehicle capacity ratio had increased and LOS had worsened. Alternative Link 1 consists of a ramp that connects the Gardner Expressway eastbound to Dawn Roadway southbound, a ramp that connects Cherry Street to Gardner Expressway, a ramp that connects Lake Shore to Gardner Expressway. The Alternative Links 2 consists of removing the elevated expressway, Lakeshore Boulevard, a ramp that connects Gardner Expressway to Lakeshore Boulevard, a ramp that connects Cherry Street to Gardner Expressway, and a ramp that connects the Dawn Roadway to Gardner Expressway westbound. Reconstruction of the Dawn River Bridge and Cherry Street lift bridge is also necessary, and a lane is added in each direction for Cherry Street as well as Willard Street. The results vary for both alternatives. There was no significant improvement in LOS, vehicle delay, or vehicle capacity ratio. The horizontal alignments were done based on the TAC manual. Certain exit and entrance ramps were designed. The design speed of 80 and 90 was analyzed.
So now I'm going to go over the 3 typical cross-section designs that were produced using AutoCAD. These cross-section designs were made in accordance with Chapter 2 of the TAC manual. The goals for these designs are minimizing area while keeping safety paramount. What you can see now is the cross-section for the redesigned Lakeshore Bridge. It includes 4 3.5 meter lanes, along with appropriate shoulders on either side. The respective 3 meter right shoulders can be used as an emergency lane. The vehicle travel directions are separated by a concrete median and a 1 meter buffer on each side. The total right-of-way for this design is 24 meters. Next is the typical cross-section for the ramps leading to and from the Gardner Expressway. It includes a single 3.7 meter lane with a 2.5 meter emergency lane on the right side. The lanes are designed with a 4% incline to allow for an increase in turning speed and horizontal friction. The total right-of-way for this design is 9.2 meters. Lastly, the regular road design was produced. This design would be used for adjacent roads, more specifically Commissioner Street. This design consists of 4 3.7 meter lanes that can safely support bus stops. It also includes a 1.8 meter sidewalk with a 2.5 meter buffer between the road to facilitate safe pedestrian travel. The total right-of-way for this design is 23.8 meters.
So this decision matrix evaluates for traffic interference, mobility level of service, vehicle delay, and vehicle capacity ratio, and as of now, the team recommends Alternative Links 2. Design challenges faced were challenges with the modeling software, data availability, and unexpected results from Vistra, which could be due to modeling errors.
Innovent is a parking system that combines conventional parking with the automatic rotary parking to give you the roulette parking system, like the ones at the casinos. There is a platform for entrance and exit, which behave like a conveyor belt and only moves when the vehicles are completely empty. The system has 2 parts. The outer ring rotates in a counterclockwise motion, like the conveyor belt at the airport. The second is the middle circle, which has 8 lifts that twist in both directions and rises and lowers itself once the vehicle is on it, and then places the vehicle in an available slot within the system. The system allows for the vehicles to enter and exit at the same time. It can hold a great number of vehicles in a small surface area above ground. The number of levels underground and the depth of excavation depend on where it will be located in the Portland's region.
The geotechnical budget for Phase 1 is outlined in this table. This design consists of 2 major elements, which were the desk study and preliminary design. The project is on track to be completed in a total of 93 days with a total cost of $876,315. The final steps remaining for this phase is to produce the final report, close this phase of the project, and prepare for Phase 2 of the geotechnical design. Next, the transportation budget is outlined in this table. This design consisted of 4 major elements, which were the traffic data collection, traffic management, preliminary design, and detailed design. The project is on track to be completed in a total of 88 days with a total cost of just under $1.3 million. The final steps remaining is to produce the final report, sign off on the design, and close the project. In conclusion, for the geotechnical services, the recommended foundation design is micropiles, and for the transportation services, the alternative ramp design 2 is recommended. The next steps are to produce the final report for the client, close Phase 1, and prepare for Phase 2 of the geotechnical services. And that concludes our presentation for Phase 1 of our engineering services for Portland's. On behalf of Iceberg Engineering, I'd like to thank you very much for listening.